Dr. Sauceda's research focuses on the development and application of machine learning-based methods to accelerate predictive materials and molecular system simulations. On the machine learning side, he is interested in the development of physics-based machine-learned force fields and physical time series, interpolation, and forecasting. On the applications part, he is interested in understanding the implications of the nuclear quantum effects on the physical properties of materials and molecular systems. So today he is going to talk about a deep learning architecture for molecules and materials. Let's welcome.
Thank you. Thanks for a nice introduction. And so this is I will mainly talk about the article that we got this award for, and I will try to paint a picture of what are the implications of that work, and give like a very big overview of what kind of do with it, especially in the case of deriving properties of materials and trying to understand better the physics of chemical systems. Okay. First of all, I'm coming from Mexico, so I always like to make it like a zoom in of where I'm working on. So I'm originally from the north of the country, close to the U.S. But I work in Mexico City. I've been living there for a bit. And this is a very nice picture that the first time I flew to Mexico City. This is the view when you arrive at night. It's fantastic. I mean, I love it. I'm originally from a very small village in the north, so to see that is very intimidating. But yeah, it's a very nice city to live. So a bit of the university. So it's a national university in Mexico. This is the largest university in Latin America, and it was built on top of a volcanic remains, let's say, of a very old volcano, like a couple of thousands years ago, and there's a very beautiful monument on one of the main rocks there. The Institute of Physics was the first Institute of Physics in Mexico. It dates to, I think, the 40s, 1940s, and at the moment we are like roughly 140 researchers, and you're welcome to visit anytime. Just send an email and then we can arrange it. So my group is so I arrived in Mexico a couple of years ago, like 2 years ago. And this is my group, and a bit of the things that we do there, we mainly focus on developing force fields for materials and biological systems. On the physics side, we apply these force fields to understand the quantum nature of materials and the implications, the physical microscopic implications. Lately, we started a big project from the theory point of view and the experimental point of view on battery physics, as well as some old things that I've been doing for over 10 years, which is metal clusters, but also some new things that I started when I arrived, which I think they are very interesting, which is dynamical processes and physics in general, either nuclear or electronic dynamical processes, and also some electronic structure, either in first and second quantization. And all this is based from always using tools from machine learning. So today we'll focus on those two topics. So I want to briefly explain what do we do in the other things. And the reality is that any, well, any dynamic process in physics can be just seen as a time series. So in that regard, so we've been using some tools such as LSTMs and other kind of recurrent neural networks to understand the dynamics, for example, of molecules at certain temperatures under certain conditions. Or, for example, we were interested in making predictions of the of the behavior of certain electronic properties of materials as a function of time, just to find correlations and so. This is some kind of some examples, and we also work on evolutions of wave functions and so. And on the electronic structure side, so we work with spin systems, quantum Monte Carlo, and in particular we got this recently. We get this very nice applications on polaritons, and this was financed by our institute. It's an experimental theoretical effort. Now the article that we got this really huge honor was this architecture is called SchNet. It's basically it's just was the first like message passing architecture applied to molecular systems, and of course I have to like put the authors there. So at the moment, most of us we were working at the Technical University of Berlin, and after this was 2017, 2018, this paper. Now we all move on. I mean, only the professors, of course, not. And so the talk I want to explain what is what was this contribution that now makes this neural network and this architecture the base for all modern architectures. So I will mention a bit what was the evolution of this and some of the applications. And in the second part of the talk, I will briefly mention other kind of models that we use for learning molecular properties, such as kernel methods and particular kernel regression, as well as some physical results, just to show what can we do with this kind of things from the physics point of view. I guess I don't have to like spend too much time in motivating why machine learning is important. I mean, you can apply it basically. It's just a set of tools, so we can apply it to any problem that we have at hand. Either for example, I like one example that I like very much is how to like better like use the management for renewable energies. This article here is I forgot the authors, but this was one of the biggest revelations, at least to me, that how can an algorithm based on machine learning can optimize just matrix multiplications and all the implications that this has, because absolutely everything uses matrix multiplication. So if we can get one order of magnitude in optimizing this operation, I mean every piece of science that is developed will benefit from this. And of course, this is a big topic right now, which is Plainable, trying to open the black box. And of course, after all, this speaks for itself. Okay, so our main interest is to learn to try to circumvent the solving the Schrödinger equation for electronic systems. Especially because it's extremely expensive. It's let's say if we have like a small molecule such as aspirin, we want to solve the compute its energy and forces, for example. Depending on the level of theory that we use, can take a couple of hours up to a couple of weeks. So if we increase the accuracy of our calculation, so if we want to actually perform let's say thermodynamically representative properties. We need like on the order of 10 to the 6 calculations of this of this type. So that is clearly unfeasible. So we have to find ways to circumvent this kind of calculations. And one of them, of course, is machine learning. So what is the state of the art of, or the state of the field, better said, is so what kind of methods do we use according to the system? Well, if we go to very small systems, we can use these ab initio methodologies, such as solving directly the Schrodinger equation. But if we want to go to more interesting systems, like to try to develop new drugs and so, we're forced to use classical force fields. And what the idea of machine learning force fields is first we start like developing methodologies for small molecules and trying to create a certain architectures or knowledge to finally reach to these bigger scales and to increase to greatly increase the accuracy of these simulations. Okay, so here this is just to show what is if we want to solve the system, the electronic system using ab initio methodologies. There are like different flavors, but this is the order of the operation that we have to do to actually solve these differential equations. Sorry? Well, depends on the approximation, but could be. I mean, if we want to order like really large, it's around maybe like 1 million of operations. But of course, it's always important the prefactor. No, that is always plays a big role. So anyway, so the thing is that in general, if we want to this is related to this and it's related to the basis that we use to expand the wave function that we want to use, as well as the number of electrons and so. But usually this, for example, full CI can be used only for molecules like for atoms and to a good approximation. And that is using like thousands and thousands of hours of supercomputing. That's why almost no one uses this methodology, and rather people focus on trying to use this with CCSDT, which is copper cluster, which is like known as the best as the gold standard of quantum chemistry. And depending on our like resources available, can take up to like from hours to days. But it's the best that we can do to do like reasonable calculations. But most of us, we use density functional theory, which is much faster and much more efficient. We sacrifice accuracy, of course. So at the end, what we want to do is to take a system that we like or that we need to simulate, and we just try to do molecular dynamic simulations, meaning that we propagate in time the Newton's equations. So what we want there is to compute all the thermodynamic properties available or that we need to calculate. And usually what we have to do is like on the order of 10 to the 6 operations. Well, calculations of the Schrodinger equation if we want to do it using ab initio. And this is clearly not feasible because if one calculation takes on the order of 10 seconds, this very quickly goes out of hand. And because of the title of the talk, well, we can assume that machine learning can can be used to solve this, to address this problem. Some couple of years ago, we got this we wrote this review where we present we don't base on the architectures and specifically but we present what will be the important things that one force the A force field has to fulfill to be meaningful and be able to represent a chemical system. And now, so how does the data that we use looks like, right? So usually the way we generate data is we run like short molecular dynamic simulations, meaning that so we have for each coordinate, like set of coordinates of the system, we have its energy, but also we have the forces acting on each one of the atoms. That is our data set. And then we sample this distribution like randomly, and with all these samples now we can use this for training our methodology or our model. Now here comes the background for the architecture. So so graphs, we all know that graphs are important. They are used like everywhere to represent. You can well, the most widely known is social networks, but can also be used to represent chemical systems. And the way graph neural networks work is that we can start with a representation for each one of the nodes, and try to propagate information through this graph. So let's say that so we have at the beginning, so we have for node number 2, we have an initial state. Is this okay? Yeah. So we can just so what we want to do here is to represent using a vector each one of the we think that these are the things are atoms. So one of the atoms. So the atoms that are similar, for example, hydrogen atoms, carbon atoms, they all will be represented by this using the same vector. But now because atoms and molecules, of course, they interact. So we want to embed this information in this representation. So how do we do it? Well, we first start with a random representation, and we can use a graph neural network to propagate this, to evolve these representations. And how do we do that? Well, we exchange messages between the different atoms, and this is done in a very direct way, which is so we use something that are called interaction layers. This is for example, if we take the vector number 3, so we construct these messages using from the atoms that are connected to that one, and using a very simple expression, we can evolve its representation according to its environment. For example, we can first we construct something that is called the aggregate operation. So we combine them, these two vectors, its neighbors, somehow, right? So after we combine them, we have to update its current state. And how do we perform this update function? Well, we do it. We can define it later, but to a higher level, it's just that this is the two operations that we use to update these representations. And after this, we have a new representation that has already information from its neighbors. And so we repeat this operation, of course, for all of the atoms in the system. And now we have a new representation. So each one of the representation already has a first pass of information from its neighbors. So we can repeat this n number of times. So until we think that is enough information propagation, because if we do it this too many times, there is loss of information. There is diffusion of information, so it doesn't contribute anymore. So we do this several times, and the general formula for this kind of networks is this one here. So, and based on the application that we have, we can define each one of the functions of update. And these are some of the most used, at least up to a couple of years ago. And these are some of the most popular versions of these networks. As you can see, they date like back to 2015. Um, and but then what is why to use these graph neural networks instead of like normal fully connected or any other architecture? Well, because in chemistry, so one of the biases that we know that we have is that interactions between atoms are hierarchical, meaning that closer atoms they interact stronger than atoms that are far away, right? So, and this is a characteristic that is inherently built in graph neural networks because of this exchange of local messages. Okay, so this is this was the main idea that was used to create this architecture, and so we went we wanted to apply this to a chemical system, and these interaction layers here are the ones that we were like talking about that use this exchange of messages, and each one of these interaction blocks is like has like several elements, but it's just to construct more nonlinearities. But the key part in this contribution, this article, was that the fact that we use convolutions as a way to obtain a continuous representation. And this idea was, I mean, this this result was is now the base for most of modern architectures, and that just know that they learn force fields. But so after a while, we realized that this kind of architecture can actually be so has some degree of interpretability, in the sense that of course, if we force the system to learn certain property, during the training process, so the system will adapt to learn this particular property that we want to learn. And because like here we use we train for learning the energy of the system. So we saw that the first part of the neural network is it constructs certain object, which is like a feature descriptor or feature representation, which is the one that encodes all the let's say the chemistry that we try to enforce in this architecture. And how do we know? Well, before going in that direction, I just want to like repeat what I showed before, which is the way that these interaction blocks work. For example, in the first interaction block, we focus on one of the hydrogen atoms, so it just like passes the information of the local environment of the other atoms, and then after the first pass of the first interaction block, it already has information of its local neighborhood. But after the second pass, so in the second interaction block, you already have information, like redundant information of the local environment. Here is a very small molecule. This will look much better in a larger system, but it is that in each pass of the interaction block, you get like information of like far and far away from this local neighborhood. And at the end, you will have like a representation that in principle has all the relevant information of the local environment. So now we can use this representation to see what was what it learned, right? And the way that you can do that is to probe this feature description, meaning that you can see the way at least we interpreted in this paper was that it gives you some sort of probability or chemical potential for the system, meaning that in this case, for example, was for hydrogen. So we put we obtained the feature descriptor, and we just put an extra hydrogen atom around it, and see how did it react this representation. And even though you cannot extract directly what is the chemistry behind, but you can see that this representation reacts in a certain way, and then we can use this representation as the input of another neural network to after that to train it to learn something else, which is actually what I consider that was the big contribution, because after this paper, other articles came that I will just show a couple of examples that they use this representation, this feature representation, to, for example, to learn like higher level properties like polar stabilities, dipolar moments, and so forth. Other properties that were not initially the energy, but now they can specialize into learning like higher, well, addition property, right? So, and can be as complicated as, for example, to learn the Hamiltonian of a molecular system. But again, the basis for all this very complicated architecture is to first construct this representation that are based on SchNet. And even in a much like in a much more complicated application was used to in the context of variational quantum Monte Carlo to solve the electronic structure, the electronic Schrodinger equation for molecules, right? And where here the SchNet architecture was used to run representation between interacting electrons and interacting electron nuclei. And yeah, that's why I was saying that this architecture became like the base for many other applications in machine learning chemistry. Later, so there is by like a work led by Oliver Unke. He took this approach into a higher level, and so he constructed this much more elaborate architecture, which is still based on the same ideas, but now this one uses equivalent representations, meaning that in all the representations that are learned in SchNet, if you have the molecule and you rotate the molecule in space, the representations are invariant, meaning that these vectors in n dimensions will not rotate, right? So, but here in this case, the representations rotate with the molecule and with the system. So for some reason that we don't know exactly, it does a much better work, a much better job in learning something, in decoding the information. And since then, a lot of other covariant or equivariant architectures have been developed, and all of them, they point in this direction that for some reason, if we impose a group representation for these models, they learn a higher level, or that it is easier to learn certain properties. Again, we don't know exactly why it works, but it works, as many things in deep learning. Okay. So just briefly to mention what we did in this work was we wanted to encode the certain properties of the system, such as the full spin of the system, but also the total charge of it, and basically, so what it does so if we have a system and we enforce this kind of electric and electronic properties, so up to a certain extent, this forces the system to adopt a certain representation, to learn something else. And how do we know that it learns something else? Well, because if we use, for example, if we probe what these feature vectors learned, if we didn't use any spin in the system, then the system doesn't react to a stimuli that we are putting there, no certain perturbations. But if we enforce the spin of the system, we know, so we see that actually the system is reacting when you try to probe it against certain perturbations. So it does benefit from this. And actually, it learns parallel surfaces and can be used, for example, also to learn excited state PES. Okay. Something else that I mentioned at the beginning was that all this exchange of local messages usually looks like this, right? So certain atoms, they will only look at the vicinity of their interactions, but we know that the quantum mechanics is not so trivial and likes to behave oddly sometimes, um, and um, and certain things that happen, like for example in a very long protein or polymer, something happens in one of the ends will necessarily affect the other end of the system. And with normal architectures, with this message passing, you don't capture this kind of effects. So here we introduce this other like no local interaction, which is based on attention, uh, which up to like up to certain extents capture this non-locality of what is going on in the system. Of course, because this is an attention mechanism, this of course takes a hit on the efficiency of the model, but has been so for example in our work, which is like battery research, electrochemical systems, they are very stringent, and so they don't. So what happens in one part of the system of the cathodes, it has huge implications on other parts on the, for example, the reactivity of certain of other parts. So this architecture has been capturing those effects to correctly describe the ion dynamics. Okay, so I will just skip this, and so this is what some of the, let's say that the branch of research that we've been doing using neural networks, but um, another part which we have been also developing is the use of kernel-based regression-based models to learn the same properties, so energies and forces. So if it is already working so well, neural networks, why do we want to move into using another tool? Well, so kernel-based regression is very efficient when using data. So what we can accomplish for certain materials using, I don't know, thousands of training data points, with kernels we can use it maybe, so we can get the same accuracy using a handful of points, let's say 10 data points, we already can reach the state of the art sometimes. And very briefly, so how does the kernel regression work? Extremely naive representation is just that we can just combine, for example, Gaussian functions to reconstruct a much more complicated function, right? And this works extremely well. I mean, of course, there is a theorem that proves that this works. But so the idea is that normal kernel-based regression basically learns the function that we actually want to learn. This is you want to learn f of x, and then you just construct your model. But in the case of what we wanted to learn, we wanted to construct forces, meaning that we need the gradient of the potential energy surface or the energy of the system. So what we did here was to generalize this model in such a way that instead of learning directly the function that we want to use, we train it on the gradients of this function. And so the great thing of kernel-based regression is extremely flexible. You can just like substitute things, and then you have to just change your covariance matrix, but that is a minor thing. And so basically now, instead of using a normal kernel, which will be, for example, the Gaussian, here we use our kernel transforming to the Hessian of the Gaussian function. And then your model, so your new model is this one here, right? So you learn the gradient of the function, of the original function. And but because everything is an analytical formula, you can just integrate this thing. And when you integrate, you recover the original function, the underlying function. So by training the gradient, you automatically recover the function f. And so we call this methodology the gradient domain machine learning, the GDML. It has been proven very successful and very data efficient, and because we're interested in on the chemical properties of all this of materials and molecules. For us, this is very convenient because it's extremely efficient using data, and so we can use it allows us to use very high level methodologies for computing the data. So over the years, we have evolved the methodology, and we have published like several papers on this. These are the main articles. First of all, in the first version was not symmetric, but then we know that molecules and materials they have to like follow certain point groups and translational groups. So after in second iteration, we just like symmetrized the kernel. Then we extended to translational symmetries, and then because kernel regression usually uses a lot of memory RAM, so we developed a numerical optimizer exclusively for this methodology. So now I will just quickly go through some of the physics, and so most of the time when people does molecular simulations, they assume that atoms are just classical particles, and in nature that is not true, and so we skip a lot of the interesting properties of the systems. And for example, the diffusion of protons in a protein under like aqueous conditions. So it is fully driven by quantum effects. So if you perform like classical simulations, you will not get the proper like transport numbers. The optical properties, they also depend on this on the nuclear quantum effects. And up to a couple of years ago, people thought that the only relevant properties that where quantum effects are like are measurable were the ones that where they studied or they depend on the protons, because protons are extremely light, so they are inherently quantum. But we demonstrated that actually the even heavy atoms, they present quantum effects. Why? Because the quantumness of the system is not based on individual atoms, but it actually delocalizes on the whole system. So any system, any system will present quantum effects even if has no light atoms. Just to give you what is an idea of which methodology do we use. Well, this is the equivalent of using classical simulations. You have a potential, and then you have a classical point particle. What we use is something that's called ring polymer or path integral molecular dynamics, where you substitute the classical particle by n copies of the same particle glued by springs. So this looks like a very cartoonish approximation, but it actually comes from the theory. When you use the path integral representation of quantum mechanics, and you do a lot of algebra, you get that to an effective Hamiltonian with no approximation. No, this one has no approximations. The only thing is that P, the number of copies, has to tend to infinity to full capture all the quantumness. Okay, but this Hamiltonian allows us to do actual simulations of this. So what are the main things to consider, or so what are the main consequences of this of the quantumness of nature? Well, if we just perform some simulations of this molecule, which is taurine, and we analyze the distributions of distances between atoms, what we obtain is that classical system will be always more local. The distribution will explore like distances shorter than it should be. While when we introduce the quantum effects, it tends to explore longer distances, meaning that has more access to the nonlinear, to the unharmonic part of the interactions. So this is this is the most crucial part to understand from all this, and we call this quantum interatomic dilation. So the same way that the thermal dilation exists, while there is an inherent part of contribution that comes from the quantum mechanics. Always is nice to see how does it look like the simulations, and basically what you see is that they look a bit like a jelly balls, like moving around, right? And this is the localization of the quantum enforced by quantum mechanics. And this same localization, what it introduces in our simulation is basically is tunneling effect, right? So all the where we used to be like high barriers, it tends to lower the effective barriers, but also in some systems, depending, it tends to localize certain dynamics, as we'll see. So we have used studied several systems under like the nuclear quantum effects and so on. But today, the only example I will present is something that nobody thought that could be possible, which is dispersion interactions. So dispersion, as I showed, so the nuclear quantum effects tends to delocalize the like immediate distances, no, for like first neighbors. But even that, the localization of first neighbors has implications of how strong is the interaction between non-bonded fragments. Okay, and actually the physics is quite straightforward. So because let's say two fragments or two systems that they don't share electrons, they interact via van der Waals forces. So, but if we analyze what the van der Waals contribution comes from, there's this coefficient, which is in this case the C6 coefficient, which comes from this integral here, and this integral depends on the polarizability of each one of the material of the components, but at the same time the polarizability depends on the effective volume of the system. So now, if for whatever reason we expand or contract the volume of where the electrons live in each one of the fragments, we necessarily will change the intensity of the interaction of the van der Waals contribution. Meaning that if we just like scale each one of the system, we will get like more intense interactions. So, and because we now know that these things, this quantum interatomic dilation exists, so necessarily there will be an increment of the intensity of the van der Waals interaction just coming from quantum mechanics. And we show this for this system, which is the dimer of benzene atoms, molecules. There was this very long, for many years, nobody knew which one was the most stable, let's say, arrangement of these two molecules. And most of people were like, well, they must be degenerate in energy. This one, which is called the T-shape, and the parallel display. And because was not able, so nobody was able to do like high-level calculations at finite temperature. So we didn't have any answer for this. So what we did was to use all these function models to train in extremely high level of theory forces, so we can perform molecular dynamics to a very accurate simulations, and then and see which one is, if there is certain preferences on this kind of interactions. So just by doing classical dynamics, what we saw is that the energies, they didn't change much. So the thermal contribution, even though prefers certain configuration, it doesn't really like changes a lot. But once you introduce the nuclear quantum effects, what you see is that it actually prefers one of them. because we have, just by the quantum effects, we have 11% increment in the strength of the interaction. Of course, in this one, in the parallel, we have like 20% because of the stacking. But what we saw is that by introducing nuclear quantum effects, we actually break this degeneracy that was thought to be there. So now what we are waiting for is an experimentalist to show actually that statistically one of the parallel displays will be more preferred than the other one. Okay, and we also saw the same by if we put some benzene molecule on top of graphene. What we saw was that also you get a more localized dynamics. This is the angle that the molecule is exploring. So because the forces are more intense, then now the molecule cannot really like stand too much. It tends to be in shorter distances. And now with this, I'll finish. So the idea of all this is we develop methods that are accurate, that represent properly the interactions in chemical systems, in order to actually understand what is going on, what is the physics and the chemistry in the system that we are interested in. And with all these tools, what we obtained was an understanding of what is going on, what are the implications of nuclear quantum effects at finite temperature in chemical systems. So what we saw is that it's a very counterintuitive result, because in general when we think about quantum mechanics is that quantum mechanics tends to delocalize properties. The system tends to delocalize. But actually dynamically, that is at 0 temperature, at 0 Kelvin, this notion of the localization of the system. But once we introduce the temperature, what happens is the opposite, because then what it does, the finite temperature combined with the nuclear quantum effects, what it does is intensify the interactions, and then because the interaction energies are more intense, so the system is less flexible now. As we show it in several examples. Now here I show the van der Waals interactions, but also when in methyl in these rotors, but also in transition, electronic transition, this effect occurs. And what is the explanation? Well, when we introduce the nuclear quantum effects, what it does is it tends to rearrange the structure of the system. But because we arrange the structure of the system, now the interactions are different, and they are more intense in general. So the fact that now the interactions are more intense, this will again rearrange the structure of the system. And if we propel this back and forth interaction by thermal fluctuations, then we obtain this new free energy surfaces for the system that is a direct consequence of the nuclear quantum effects of our system. And with this, I finish, and well, thank you.